Types of unit cells. Based on the position of constituent particles in a unit cells are broadly classified into primitive unit cell, centered unit cells. Primitive unit cells. When constituent particles are present only on the corner positions of a unit cell, it is called as primitive unit cell. It is denoted by the letter P. Centered unit cells. When constituent particles are present not only at the corner positions, but also at some other positions within the crystal, then the cell is known as centered unit cell. Centered unit cells are further classified into body-centered unit cell, face-centered unit cell, end-centered unit cell. Body-centered unit cell. In this type of unit cell, one constituent particle, such as atoms, molecules, or ions, is present at the center of the unit cell, in addition to the particles present at the corner positions. Body-centered unit cell is denoted by the letter I. In face-centered cubic unit cell. In this type of unit cell, the constituent particles are present not only at the corners, but also at the center of each face of the unit cell. Face-center unit cells are denoted by the letter F. Calculations of number of particles in a unit cell. A crystal lattice is made up of a very large number of unit cells. Each unit cell is touching a number of other unit cells. In a unit cell, every lattice point is occupied by one constituent particle. Thus, a constituent particle present at the lattice point may be shared by a number of unit cells. Let us now understand the contribution of a particle in a lattice point to its unit cell. A corner atom is shared equally by 8 unit cells. 4 unit cells are present in the lower layer and 4 unit cells are present on the upper layer. Therefore, each corner atom contributes only 1/8 atom to a particular unit cell. A face-centered atom is shared equally by 2 unit cells, having a common face. Therefore, an atom present at the center of the face of a unit cell contributes half atom to each unit cell. A body-centered atom is not shared by any adjacent unit cell in a crystal lattice. Therefore, it contributes fully to a unit cell. A edge-centered atom is shared by 4 adjacent unit cells in the crystal lattice. 2 unit cells are present in the lower layer and 2 unit cells are present on the upper layer. Therefore, it contributes only 1/4 of itself to a unit cell. Calculation of number of atoms per unit cells in primitive cubic unit cell. Simple cube. In simple cubic unit cell, there are 8 corners in a cube. There is 1 atom at each corner of the cube. Since each corner atom is shared equally by 8 unit cells, hence, each corner atom contributes 1/8 atom to each unit cell. Number of atoms in one simple cubic unit cell is equal to 8 into 1/8, which is equal to 1 atom. A simple cubic unit cell contains 1 atom. Calculation of number of atoms per unit cells in body-centered cubic unit cell. In a body-centered unit cell, there are 8 atoms at each corner positions and 1 atom at its body center. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of those 8 corner atoms to the unit cell is 1 atom. The atom at the center of the unit cell is not shared by any other unit cell. Thus, its contribution to its unit cell is whole. Hence, the number of atoms per body-centered unit cell is 1 plus 1, which is equal to 2. 8 corner atoms into 1 by 8 is equal to 1 atom. 1 body-centered atom is equal to 1 into 1, which is equal to 1 atom. Therefore, number of atoms per unit cell is equal to 2 atoms. Thus, a body-centered cubic unit cell contains 2 atoms of an element. Calculation of number of atoms per unit cells in face-centered cubic unit cell. In a face-centered cubic unit cell, there are 8 atoms at the corner positions and 1 atom at the center of every face of the cube. As each atom at the corner position contributes 1/8 to the unit cell, the contribution of these 8 corner atoms to the unit cell is 1 atom. Each atom at the face center is shared between 2 adjacent unit cells. Thus, the contribution of 6 such face-centered atoms to the unit cell is 6 into 1 by 2, which is equal to 3. Therefore, the total number of atoms per face-centered unit cells is 1 plus 3, which is equal to 4. 8 corner atoms into 1 by 8 is equal to 1 atom. 6 face-centered atoms into 1 by 2 atom per unit cell equal to 6 into 1 by 2, which is equal to 3 atoms. Therefore, total number of atoms per unit cell is equal to 4 atoms. The face-centered cubic unit cell contains 4 atoms of an element. The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in 1 dimension. In 1 dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in 1-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of 1-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed packed layer A. Notice this layer has triangular voids. Place a similar closed packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B-type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the six surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A-type and the second layer as B-type, then the third layer will also be A-type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal closed packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12. Structures of some ionic compounds. Structure of sodium chloride, NaCl, rock salt structure. Sodium chloride crystal is made up of sodium ions, that is, cations, and chloride ions, that is, anions. Sodium chloride crystal is a face-centered cubic close-packed structure. The chloride ions, being comparatively larger in size, occupy the corner and face-centered positions. The sodium ions, being smaller in size, goes to fill up the voids. Thus, sodium ions occupy the octahedral voids in cubic close structure. On extending the structure, we will see that each chloride ion is surrounded by 6 sodium ions, while each sodium ion is surrounded by 6 chloride ions. So the coordination number is 6. Now, let us calculate the total number of ions per unit cell. Total number of chloride ions per unit cell is equal to sum of chloride ions at corners and at face centers. The total number of chloride ions is equal to 8 corners into 1 by 8 per corner plus 6 faces into 1 by 2 per face, which is equal to 4. The total number of sodium ions per unit cell is equal to sum of sodium ions at the 12 edges and 1 at the center of the cube. The total number of sodium ions is equal to 12 edges into 1 by 4 per edge plus 1, which is equal to 4. Thus, the unit cell of NaCl contains 4 chloride ions and 4 sodium ions. Structure of cesium chloride. Cesium chloride crystal is made up of cesium ions, cations, and chloride ions, anions. In cesium chloride body-centered cubic lattice structure, the chloride ions are present at the corners of the cubic lattice, while cesium ions are present at the center of each cube. The reverse is also possible, which means that cesium ions can occupy the corner positions, while the chloride ions can occupy center of each cube in the crystal lattice. If we consider the first structure, in which chloride ions occupy the corner positions while cesium ions occupy the center of each cube, then we will notice that each cesium ion is touching 8 chloride ions, and each chloride ion is touching 8 cesium ions. So, the coordination number is 8. Now, let us calculate the total number of ions per unit cell. The total number of chloride ions per unit cell is equal to chloride ions at corners. The total number of chloride ions is equal to 8 corners into 1 by 8 per corner, which is equal to 1. The total number of cesium ions per unit cell is equal to cesium ions at the body center. The total number of cesium ions is equal to 1 into 1, which is equal to 1. Packing efficiency in crystals. The particles such as atoms or ions or molecules in crystals can be packed together in several different ways. In each type of packing, there is always some vacant space in between the constituent particles in the form of voids. We know that there are two types of voids in a packing: tetrahedral voids and octahedral voids. Thus, in a packing, only a part of the total available space is occupied by constituent particles. The percentage of the total space filled by the particles is called packing efficiency. Different types of packing arrangement have different packing efficiency. Now, let us calculate the packing efficiency in different packing arrangements. Packing efficiency of simple cubic lattice. In simple cubic unit cell, the 8 atoms or particles or spheres occupy the corner positions. Therefore, the particles are in contact with one another along the edge. The number of atoms per unit cell in simple cube is only 1. Each atom is considered as one sphere. Volume of the one atom or one sphere is equal to 4 by 3 pi r cube. Let A be the edge length of the unit cell and r be the radius of sphere. The spheres at the corners are touching each other. Then we have edge length A is equal to 2r. The volume of cubic unit cell is equal to A cube, which is equal to 2r whole cube, which is equal to 8r cube. Percentage of the space occupied by spheres or packing efficiency is equal to volume of one atom divided by volume of cubic unit cell into 100%. Packing efficiency is equal to 4 by 3 pi r cube divided by 8r cube into 100, which is equal to pi by 6 into 100. Packing efficiency is equal to 52.36%, which is equal to 52.4%. The vacant space available in simple cube is equal to 100 minus 52.4%, which is equal to 47.6%. Packing efficiency in HCP and CCP structures. face-centered cubic unit cell. Let us calculate the efficiency of packing in CCP structure. Cubic close packing is same as face-centered cubic packing. In this type of arrangement, the particles are touching one another along the face diagonally. Let the edge length of the unit cell be A. The radius of each sphere be R, and the face diagonal be B. AC is equal to B, which is equal to 4R. Now, let us calculate edge length A by applying Pythagoras theorem. In triangle ABC, AC square is equal to BC square plus AB square. B square is equal to A square plus A square. B square is equal to 2A square. Therefore, B is equal to square root 2A is equal to 4R. Therefore, A is equal to 4R by square root 2, which is equal to 2 square root 2R. Volume of the cubic unit cell is equal to A cube, which is equal to 2 square root 2R whole cube. We know that each unit cell in face-centered unit cell or CCP structures have 4 spheres or atoms. Volume of the 4 spheres is equal to 4 into 4 by 3 pi r cube, which is equal to 16 by 3 pi r cube. Now let us calculate packing efficiency. Packing efficiency is equal to volume occupied by 4 spheres in the unit cell into 100 by total volume of the unit cell percentage. Packing efficiency is equal to 16 by 3 pi r cube into 100 by 2 square root of 2 r raised to whole cube percentage. Packing efficiency is equal to 16 by 3 pi r cube into 100 by 16 square root of 2 r cube, which is equal to 74%. HCP or CCP has a packing efficiency of 74%. Efficiency of packing in body-centered cubic structures. In a body-centered cubic structure, there is a particle at the center of the unit cell, in addition to particles at the corners. Thus, in a body-centered cubic structure, there are 3 spheres in contact with each other along the body diagonal. Let A be the edge length of the cube and R be the radius of the sphere. The body diagonal AF is equal to C, and face diagonal FD is equal to B. Then AF is equal to C, which is equal to 4R. Now let us calculate the body diagonal C and face diagonal B. Using these values, we can calculate A. Let us consider the triangle EFD. By using Pythagoras theorem, we have FD square is equal to EF square plus ED square. B square is equal to A square plus A square. B square is equal to 2A square. Therefore, B is equal to square root of 2A. Now, in triangle AFD, AF square is equal to AD square plus FD square. C square is equal to A square plus B square. C square is equal to A square plus 2A square, which is equal to 3a square. C is equal to square root of 3a. But C is a body diagonal which is equal to 4r. Therefore, C is equal to square root 3a, which is equal to 4r. A is equal to 4r by square root of 3. Volume of the unit cell is equal to a cube, which is equal to 4r by square root of 3 raised to whole cube. In body-centered cubic unit cell, the number of particles per unit cell is 2 atoms. Each atom is considered as one sphere. The volume of 2 atoms is equal to 2 into 4 by 3 pi r cube, which is equal to 8 by 3 pi r cube. Packing efficiency is equal to volume occupied by 2 spheres in the unit cell into 100 by total volume of the unit cell percentage, which is equal to 8 by 3 pi r cube into 100 by 64 by 3 square root of 3 r cube percentage, which is equal to 68%. Packing efficiency is equal to 68%. In body-centered cubic unit cell, 68% of unit cell is occupied by atoms and the rest 32% is plain empty space.